Good morning. So I would like to officially welcome you to Calculus 2, that is integral calculus. If you are here in this subject, that means you have already finished Calculus 1 or differential calculus. So the importance of differential calculus in integral calculus is very prominent, especially when we now try to relate the two subjects together. So in your course outline that I have given you, you'll notice there that there are some similarities between differential calculus and integral calculus when it comes to the formulas that were used for the two subjects. Okay, so our module for today is introduction. So I'm just going to introduce to you what integral calculus is, what are the two different types of integration. Okay. By the way, this presentation is co-presented by me and another co-faculty of mine. So in this unit, here are the things that we need to have an understanding of. Okay, so here are the following desired learning outcomes. Number one, we must understand the principle of integration. Number two, we must relate differentiation and integration. And number three, we must identify the general properties of the indefinite integrals. So indefinite integrals, okay, is the first topic for integral calculus. Later on, we're going to develop skills in processes in solving now definite integral. So what is the difference between indefinite and definite? We're going to see as we go along the course. So after this unit or after this video, these are the principles or the learning outcomes that we must have. So the indefinite integral. We have been occupied up to this point with the problem given. So given a function, to find its derivative or differential. Many of the most important applications of the calculus lead to the inverse problem wherein given the derivative of a function to find the function itself. The required function is called an integral of the given derivative. And the process of finding it is called integration. So the given function is the integral. So between differential calculus and integral calculus, okay? So in differential calculus, we have a function, we derive its differential, but here in integral calculus, we have the differential of the function and we find or we integrate to get the original function that was derived, okay? So for example, differential calculus, let's say, is going down and integral calculus is going up. So if we continue, if small letter f of x is a given function and capital F of x is a function whose derivative is small f of x, the relation between them is expressed by writing. So this is our equation. Capital F of x is equal to, this is called the integral sign of the small letter f of x, differential of x, or dx, where this sign again is called the integral sign. This indicates that we are to perform the operation of integration, no longer differentiation, upon f of x dx. That is, we are to find a function whose derivative is small letter f of x or whose differential is f of x dx. Notice the difference between a derivative and a differential. A derivative is always in terms of the functions only. Meanwhile, a differential has a differential term of the variable. So if you have your function in terms of x, you'll have differentials of x. If you have your function in terms of y, you'll have differential of y. Derivatives do not have or no longer have their differentials because they were already factored out. Okay, so I hope you learned that in your differential calculus. For reasons that will appear later, we'll always write after the integral sign the differential f of x dx, okay, rather than the derivative fx. So here in integral calculus, we're going to write the differential. So you'll notice in our formulas later on that all of the formulas has now the term the differential of the function. This is actually a very important, okay, factor in our operations. So we're using the differential again, not the derivative. So for example, let's try to evaluate the integral of x squared dx. Okay, so since, take note of this, differentiation reduces the exponent by 1, Integration, therefore, must increase the exponent by 1 in order that, upon differentiating our answer, we may return to the original exponent. So remember what I said, that differentiation, correct, is given a function, deriving it, and arriving with the differential or derivative. What happens to the exponent of the function? It usually goes down, correct, or it goes down 1 degree. So if you try to differentiate x squared, the differential will have only x. If you try to differentiate x raised to 4, the differential will only have x cubed. But since, okay, integration is the opposite or the inverse process of differentiation, if we try to integrate x squared, it must go up to x cubed, so that when you differentiate x cubed again, it goes back to x squared. So differentiation goes down 1 degree, integration goes up. Okay, so thus our first guess at the answer might be x cubed. Okay, so it's a guess. We don't have any formula yet for the integral of functions. But since we know that integration goes up 1 degree, if we integrate x squared, it should go up 1 degree. So the degree of the answer should be x cubed. Okay, so since, take note here, this is our guess, the differential of x cubed is equal to 3x squared dx. This is not the function that we're trying to integrate. So our goal is to arrive, when we find the integral, if we derive back, we go back to the original function. And your guess, x cubed, if you derive it, okay, it does not go back to x squared dx. It goes to 3x squared dx. There is an unwanted factor, 3, okay, present in your guess. So to correct this, so we want to amend this, we amend our first guess by dividing by 3. So if you want the 3 to be gone, correct, because that is the factor that is making your answer wrong or your guess wrong, you divide the equation by 3. So if you divide the equation by 3, you remove, okay, the 3 here, but you divide 1/3 x cubed by 3 as well. So dividing both sides of the equation by 3, we now have the differential of 1/3 of x cubed, not just x cubed, is equal now to x squared dx. But the addition of any constant, whatever, to 1/3 x cubed does not alter the differential. So we'll go to this later. So here, we now have a confident answer for the integral of x squared dx. So if you see, unlike x cubed, if you derive x cubed, it becomes 3x squared. We have, what? 3 as an unwanted factor. But if we derive 1/3 x cubed, if we derive it, that is 1/3 multiplied by 3 times x 3 raised to 3 minus 1. So 3 times 1/3 cancels out. It only leaves you with x squared dx. So that is now the integral of the function, meaning the integral of x squared dx is in fact 1/3 x cubed. Okay. Now there's a statement here that says the addition of any constant, whatever, okay, to 1/3 x cubed does not alter the differential. Okay. What does that mean? If I derive, so this is our differential for x squared, correct? The integral of x squared, 1/3 x cubed. If I derive this, it becomes x squared. But remembering your differential calculus, if you recall, the derivative of a constant is always 0, right? So any real number or any constant that is to be derived or differentiated will result to an answer that is 0. Meaning, for example, originally, 1/3 x cubed has plus 1. So if you derive 1/3 x cubed plus 1, it goes back to x squared dx, right? So there is a possibility of a constant being added to your integral. But who's to say that 1/3 x cubed plus 2 is not x squared dx? It will be the same, correct? 1/3 x cubed plus 5, 1/3 x cubed plus 6. Whatever constant is added into your integral, when you derive it back, it will give you the same answer. Okay, so to uncertainty, okay, we add now c. C is now the arbitrary constant of integration. So the arbitrary constant of integration lets you know that there's a possibility, or there is, okay, a chance that a constant was originally present in our equation. Now c stands for now any constant value that is to be added to your integral. The reason why, the principle that we don't know the value of c, we are not definite about it, gives us the idea of the indefinite integral. The reason why it's indefinite is because we're not really sure what this c is. Okay, so the uncertainty makes it an indefinite integral. All of the answers in indefinite integral must contain the letter c or plus c, denoting the arbitrary constant. If you do not include plus c here, okay, that is a wrong answer or wrong description of the answer. Okay, so here you have integral of x squared dx is equal to 1/3 x cubed plus c. Okay, where c is an arbitrary constant. So this equation is equivalent to the statement that, so the differential of the integral 1/3 x cubed plus c, not only 1/3 x cubed, is equal to our x squared. Okay, so there you have it. That is the principle of integration. Now, for integration, as we go along with our discussions, there are some properties that you must be aware of. Don't worry, these properties are quite similar to the properties of differential calculus. Okay, so for indefinite integrals, these are the properties that you should be aware of. So number one, so the integral of the differential of u stands for a function. Okay, so the differential of u is equal to u plus c. So this is the concept of integral calculus. Okay, so if you integrate the derivative or the differential of a function, you arrive to the original function itself, plus, of course, the constant of integration. Number two, here you have the terms integral of quantity du, function, plus dv, another function, plus dz, another function of different variables, okay, can be expressed as the integral of du plus integral of dv, and then plus integral of dz. So what does this tell you is that if the integrand consists of a sum of terms, each term may be integrated separately. So you can distribute the integral process, okay? And last but not the least, a here, so the integral of a du, a being a constant value, okay, can be written as a, then multiplied by the integral of du. So a constant can be factored out of the integration process. So if the integrand contains a constant factor, the factor may be written before the integral sign. So these are the very basic properties or general properties of indefinite integrals that you should be aware of. So the integration concept, the distributive property of the integration process, and then the factoring out of constants out of the integration process. Okay. Before we end the unit, let us review some concepts that you should have learned or that were discussed throughout the video. So first, take note, integration is the inverse of differentiation. Okay. Differentiation reduces the exponent by 1. Integration must increase the exponent by 1. And then C, of course, is our constant of integration. It is a specific component of indefinite integrals. So all answers in indefinite integrals must contain the term plus C. Okay? So here is your introduction for indefinite integrals. The next unit will discuss the basic formula or the basic formulas for integration. Okay? So if you have any questions, you can leave them on the comment section down below. So I hope this was very helpful. Thank you.